In this problem, we are looking at boom of OC. It's fixed around there at O. Two cables, D, A, and CB. We know the tensions in each one. And what we want to do is calculate the moment about that base point O in each case for B, C, and for AD. And we're looking for the force of the cable on the boom. That's a very important point. So for this one here, for BC, we're really looking at this force right here. This is the direction of the force for BC. The direction of force there for AD is this one. This is the force on the boom due to the cable. BC is acting at C, AD is acting at D. First thing that we need to do, though, is before we can write out the forces as vectors, we need to write the unit vectors. So, for example here, if I want to write out the unit vector for CB, that unit vector is going to be going from C to B. So this is ECB. And we find that by taking the journey there from C down to B. That's 2D in the positive x, D in the minus y, and 4D in the minus k. Divide by the distance, 2D squared plus D squared plus 4D squared. So that's going to be equal to 2 over square root of 21 in the I. It's going to be minus 1 over square root of 21 in the j, and the unit vector contribution in k is going to be a minus 4 divided by the square root of 21. The second cable is given to us in a slightly different way, that information, because whenever I look here at the unit vector which points from from D to A, like that. I'm given in terms of two angles. So the first thing I'm going to do is project that onto the XY plane. That projection is going to be this amount here, which is going to be equal to sine of theta. The projection onto the Z component is going to be this amount here, and that of course is equal to cosine of theta. But what I really need to do is project now the sine theta onto x and y. So this projection then is going to be that hypotenuse, which is sine theta times sine of phi. Do I have that right? That's going to be, yeah, sine of phi. And then the projection onto the y direction, that's going to be that sine of theta times cosine of phi. So don't try to remember any formulas from class, but just actually look at what those projections are. So the unit vector, which goes from D to A, in the x direction, what did I end up with? And ended up with a minus sine theta, sine phi. In the y direction, I ended up with a positive sine theta, cosine phi. And in the z direction, it's a minus cosine. So, for part A. Part A, I want to know the moment about O due to a force which is applied there at point C. So I'm going to go from the point of interest to the point of application and cross that with the force, which is going to be the tension, times ECB. The vector which goes from O to C, according to our figure, is going to be equal to 4D in the K crossed with ECB, so that's going to be T divided by the square root of 21, 2I minus J, and minus 4K. And so when I cross this through, I'm aware that any vector crossed with itself is a zero, so I'm not going to get any contributions from there. But I do have a K cross J. We know that K cross J is a minus I, so that minus and a minus makes it a plus 4D over square root of 21. I'm sorry, I'm going to factor out my D. So this is a 4 over square root of 21. And then the K cross I. K cross I is a positive J, so that gives us 8 divided by the square root of 21. And so this is going to be, what did I say that was? The K cross I is a J, and then this was a positive I, and this gets multiplied by T times D. So that's the moment about O due to this force being applied there at C. The next thing we want to do is find the moment about O, but now due to the force there in the cable AD. The R vector in this case goes from the point that we're interested in, O, to the point of application D. So this goes from O to D, cross with the vector of 2T times E D to A. We've already found that. So going from O to D, that's just 2D in the K, cross with 2T, and EDA, we have this longer expression here, minus sine theta, sine phi, that's in the I, sine theta, cosine phi, minus cosine theta in the K. Again, I know that the K cross K will make no contribution. In the I direction, the K cross J is a minus I, so this becomes a minus 4 sine theta cosine phi. That's the I component. We have a K cross I, which is a J, but we already have a minus sign, so this becomes a minus 2 sine theta sine phi. Times TD, and that is not complete because I failed to write down my J, so let me squeeze out a little space here, put in a J, and that's a T times D, and that's the answer there for B. So in each case, what we needed to do was write out the unit vector that represents the direction of the forces of the cables on the boom. So that's ECB is shown, EDA is shown. To find the moment about O due to BC, then we needed to take the vector from O to C, and then for the force there in cable AD, we go from O up to D. In each case, we take the cross product of R with F. Take great care when we carry through our cross products that we get the right numbers and the right signs to go along with those components.